Okay. We've got 11 people. All right. Okay, I'm going to go ahead and get started here. I'm going to share my screen. Right, hello everyone. Okay, a quick review of what we covered last time in terms of alkyl halides. Okay, in this chapter, we're only going to be concerned with alkyl halides. Aryl halides, we'll talk about those next semester. Both aryl and vinyl halides react very differently from alkyl halides. Okay, the key to how they react is that the carbon-halogen bond is very polar. And that means that the carbon end is electropositive and subject to attack by electron-rich species, nucleophiles. All right, so we introduced the idea of naming alkyl halides. We're going to learn naming of various functional groups. Halogens are way down there at the bottom as far as priority. Okay, we'll look at functional groups in approximately ascending order of priority. Okay, for example, if you had an alkene, that would take priority over alkyl groups and halogens. An alcohol would take priority over the alkene, and so on. Okay, so a chlorine as a substituent is a chloro. A fluorine as a substituent is a fluoro. Many alkyl halides have common names by which they're commercially known. These are just some examples: isobutyl bromide, sec-butyl bromide, and tert-butyl bromide. Okay, these are some common solvents: methylene chloride, chloroform, and carbon tetrachloride. It is important that you be able to recognize classifications, because this will allow you to predict the type of reaction and relative rates of reactions that are likely to occur. Okay, so halides are classified according to the number of carbon atoms directly bonded to the carbon which is bonded to the halogen. Okay, so here we have a methyl, a primary, a secondary, and a tertiary halide. Okay, and actually if we go back to here, isobutyl is a primary, sec-butyl is a secondary. Okay, this carbon with the halogen on it is bonded directly to two other carbons, and tert-butyl bromide is a tertiary. Okay, we'll see these terms again in our chapter on alkenes, but a geminal dihalide is one in which we have two halogens on the same carbon. A vicinal dihalide is one in which the halogens are on adjacent carbons. Okay, we talked about uses of alkyl halides, anesthetics, freons, pesticides. Okay, because of the dipole moments, this gives rise to the characteristic reactivities. Okay, carbon tetrachloride, although it has polar bonds, these all cancel each other out, and so the molecular dipole moment is 0. Okay, again, moving quickly, I covered most of this last time. Branching will lower the boiling point branching of the carbon chain. Alkyl halides have higher boiling points than alkanes because they are polar and because of the greater molecular weight. Okay, as far as densities, alkyl chlorides and fluorides are less dense than water. If you have 2 or more chlorine atoms, those are going to be more dense than water. We saw that in the extraction lab. Dichloromethane was denser than water. Alkyl bromides and iodides are going to be more dense than water. Okay. We did talk about in chapter 4 free radical halogenation. Okay, not always the best way to prepare alkyl halides unless all of our hydrogens are equivalent, as in cyclohexane. Although bromination is much more selective. So in the case of isobutane, we can selectively prepare tert-butyl bromide in good yield. Okay, but if we have something like hexane, we're going to get all possible substitution products. So that's not a good strategy for making an alkyl halide. The allylic position is 1 carbon removed from an alkene. And this goes, when you use N-bromo-6-enamide, this goes through a free radical. And let me back up here. The free radical is resonance stabilized. Okay, so this is why bromination occurs at this position. Okay, we produce a very stable allylic radical. All right, I think this is probably about pretty close to where we left off. Okay, we're going to look at 2 broad types of mechanisms. There are 2 types within each one of these, but the main reactions of alkyl halides are substitution and elimination. In substitution, okay, one group merely replaces the halide. Okay, there's no change in bond order. In elimination, we get an alkene. All right, we get removal of a hydrogen and a vicinal halogen. This is also called beta elimination. Okay, this is the alpha carbon, the halogen's on, the next one is the beta, and this is a beta hydrogen. Right, in the SN2, there's a bond broken and a bond formed at the same time. Okay, so this is how the SN2 mechanism works. Okay, the nucleophile attacks from the backside. The carbon-oxygen bond is formed at the same time as the carbon-iodine bond is broken. The 2 comes from this bimolecular transition state. Right, so both the OH and the iodomethane are involved in making up this transition state. Okay, it also happens to be a second order kinetically. Okay, so this is the rate law. Okay, if we were to use the method of initial rates, we could prove this was second order. For example, if we kept the nucleophile constant double the concentration of the alkyl halide, that would double the rate. Okay, there's only one step, no intermediate. Again, these are just a few of the many functional groups that we can prepare from alkyl halides using the SN2. Nucleophilic strength. This refers to the rate of nucleophilic attack. Okay, so it's a kinetic concept. Strong bases are strong nucleophiles, but not all strong nucleophiles are basic. A good example of that is iodide, I-, okay, which is down here in the lower right corner. Okay, this is a weak base, but it's a strong nucleophile. Okay, these are weak nucleophiles over here on this side, moderate, and that's strong. Okay, so the stronger the nucleophile, the faster the reaction in an SN2. Okay, basicity is actually an equilibrium concept. Okay, it's the equilibrium for abstracting a proton. Nucleophilicity is a kinetic concept. It involves the rate of attacking a carbon. Okay, the conjugate base is always a stronger nucleophile than its conjugate acid. So hydroxide would be stronger than water, for example. NH2- is stronger than ammonia. And then there are some periodic trends. As we go down a column, okay, comparing similar species, nucleophilicity goes up. And okay, if we compare, for example, similar negatively charged series as we go across a column, nucleophilicity goes down. So NH2 is minus is the strongest, followed by OH, followed by fluoride, for example. Okay, this is a comparison of fluoride versus iodide. Fluoride is what we call a hard nucleophile. The charge is very concentrated. It's a small ion. And in the transition state, there's not a lot of bonding. In the case of iodide, the iodide is what we call soft. The electron cloud is fluid. It's polarizable, and there's more bonding that takes place in the transition state. It can bond from a farther distance. Okay, let me go through solvent effects again. Okay, polar protic solvents can hydrogen bond. They're hydrogen bond donors and acceptors. And in SN2 reactions, they surround or solvate the ion, okay, if our nucleophile is negative, okay, as shown here with fluoride. Okay, so fluoride has to shake loose these solvent molecules before it can attack, so that's going to slow down the reaction. Yeah. A polar protic solvent is one that can hydrogen bond. It's a hydrogen bond donor and acceptor. Okay, so examples of protic solvents would be water. It can accept hydrogen bonds and donate hydrogen bonds. Liquid ammonia could be a protic solvent. Ethanol and methanol. Acetic acid. Okay, so these are examples of protic solvents. Okay, they have an OH or an NH bond, so that's what you look for. Okay, an aprotic solvent, okay, is a polar compound, but notice it lacks the NH or OH. So these can accept hydrogen bonds, but they can't donate hydrogen bonds. Okay, so acetonitrile could accept a hydrogen bond from water, for example, but it can't donate. Okay, and many of these solvents can do a pretty good job of dissolving substances. Okay, and because the aprotic solvent won't surround or solvate, let's go back to this. Okay, this is going to be slowed down because the fluoride has to break free of those solvent molecules before it can attack. In an aprotic solvent, the nucleophile doesn't have to do that. Okay, the solvent molecules don't bind tightly to it, and so it can react. Many nucleophiles can react as much as 1,000,000 times faster. Okay, this is one way of getting ionic compounds to dissolve in organic solvents, is to use a crown ether. Okay, so another factor is the leaving group ability. Okay, so we've talked about nucleophilic strength. That can affect the rate of a reaction. Leaving group ability can definitely affect the rate of a substitution reaction. Okay, so the best leaving groups are electron withdrawing, so they can polarize the carbon atom. They're stable, that is, they're not a strong base once they've left. They're polarizable, so as to stabilize the transition state. Okay, so these are some examples of common leaving groups. Okay, so the halides, you can also have sulfonates, sulfates, phosphates as leaving groups. Also some neutral molecules, such as water, alcohols, amines, and sulfides. In Thursday's lab, we're going to do a substitution reaction, and water is actually going to be the leaving group in that reaction. Okay, hydroxide is a strong base, so hydroxide is a very poor leaving group. Okay, another factor is the structure of the substrate. Okay, so the order of reactivity for SN2 reactions is methyl substrates are the fastest, followed by primary, then secondary, and then tertiary substrates really don't undergo SN2 at all. Okay, they are too crowded. We call that steric hindrance. Okay, so here's a table of relative rates. And this is for Okay, it doesn't say what the nucleophile is. But the relative rate should be the same. Okay, so 2-bromopropane is used as the standard here. It's assigned a value of 1. And, okay, it's a secondary halide. So a primary halide, like bromoethane, reacts 50 times faster. Bromomethane reacts greater than 1,000 times faster. Okay, when we go to a tertiary halide, like tert-butyl bromide, 2-bromo-2-methyl-propane, okay, that is more than 1,000 times slower than 2-bromopropane. Okay, here we have butyl. Okay, butyl is a primary, so it reacts 20 times faster. Isobutyl is a primary, but notice it doesn't react that much faster. Okay, there's some crowding on this carbon right here, so that's going to slow down the reaction. Neopentyl is also a primary, but the backside is just so crowded that it's not going to react, at least by SN2. Okay, so the more crowded the backside of the carbon is, the slower it will react by SN2, because the rate depends on how quickly the nucleophile attacks. Okay, so here's a comparison of primary, secondary, and tertiary. The secondary is slower than the primary, and the tertiary is prohibitively slow. Right. There are some stereochemical changes, definite stereochemical changes in the SN2 reaction. Okay, here we're starting with a chiral substrate. This is S2-bromobutane. Our nucleophile is hydroxide. And here's the transition state. Okay, the bond forming and the bond breaking are 180 degrees apart from each other. And the product here, okay, notice that it is R. Okay, so this started out as S, and it's been completely inverted. And so our product is R-butan-2-ol. So it turns inside out. This is called the Walden inversion. All right, so the nucleophile attacks from the back. All right, let's look at the basics of the other type of substitution reaction. This is called the SN1, and the SN1 will be that will be the basis for the lab next week. We're going to do an SN1. This is a unimolecular nucleophilic substitution. That's where the 1 comes in. It goes through a carbocation intermediate. The rate is first order kinetics. Okay, it depends only on the alkyl halide, the substrate. And it would be 0 order in the nucleophile. Okay, the stereochemical change, if there is a chiral center attached to the halogen, racemization would occur. Okay, if there's not a chiral center, you wouldn't be able to tell. Okay, so instead of a bond forming and a bond breaking at the same time, we have a sequential reaction. Okay, the bond breaks between the carbon and halogen, as shown here, and then the nucleophile donates a pair of electrons to the carbocation intermediate to form a bond. So it's stepwise. Okay, so the SN2 occurs in one step, the SN1 occurs in 2 steps. Okay, so here is one example. Okay, here we have 1-iota 1-methyl cyclohexane. First step is formation of a carbocation, and this is the slow rate determining step. Okay, the second step, this is being done in methanol. Second step is the methanol attacks. Okay, methanol is probably also being used as a solvent. Okay, and since oxygen has 3 bonds, it will carry a plus charge. Okay, so it's the oxygen that bonds, the hydrogen and the methyl are still attached. And then the next step is abstraction of a proton. Okay, this equilibrium is favored because typically when this is carried out, there's a large excess of methanol. So that's going to shift it to the right.
Did you say extraction of the proton? Or...
Abstraction of a proton. Yeah, that's what we're doing here. Abstraction. Okay, so this is removing this proton right here. Deprotonation. Okay, so this occurs if the nucleophile is neutral. Okay, so this looks a little bit different from the SN2 diagram. There is an intermediate, okay, which is this local minimum right here. Okay, an intermediate is something that is produced in one step and consumed in a second step, subsequent step. Okay, there's 2 transition states, 2 activation energies. First step is going to be the slow step. And since the nucleophile attacks in the fast step, that's why it doesn't occur in the rate law. Okay, this carbocation is so electrophilic that it will accept a pair of electrons from just about anything that can donate. And this occurs very rapidly. Well, the order of reactivity for an SN1 is just backwards from the SN2. Okay, so a tertiary substrate is the fastest, followed by a secondary. A primary is going to be really slow, and methyl is going to be prohibitive. And the governing factor here is not steric hindrance, but it's the carbocation stability. Okay, that's going to be the governing factor. A better leaving group is going to increase the rate of the reaction. Okay, this is something we saw back in chapter 4. We had a brief introduction to reactive intermediates. A tertiary carbocation, okay, is stabilized by the inductive effect. Okay, these methyls are pushing electrons toward this electron deficient carbon. And it is also stabilized by hyperconjugation. Okay, so there is a kind of a pseudo pi bonding that takes place between this empty orbital and this sigma bond. Okay, and that helps stabilize the carbocation. Okay, and if we had 3 of these methyl groups, all 3 of them would help stabilize. Okay, so the more carbons you have bonded to the carbocation, the more stable it is. Solvent is important in SN1 reactions. Okay, this time you want a polar protic solvent. Okay, you can do a SN2 in a polar protic solvent, but a polar aprotic solvent works better for an SN2. Okay, in this case, the first step is ionization. And if you solvate the ions, that is, surround them with solvent molecules, okay, that slows the rate at which they can come back together. Okay, this reaction is reversible. Okay, but if we solvate the ions, that helps to separate them. Okay, both the cation and the anion are solvated here. With an aprotic solvent, just the cation is solvated. Okay, so a carbocation is sp2 hybridized. It has a trigonal planar geometry. It has an empty p orbital, which is perpendicular to the sigma bonds. And here we're starting out with a chiral substrate. Okay, 4 different groups. We've got bromine, methyl, ethyl, and isopropyl. And our starting material has the S configuration. Okay, when bromide leaves, this intermediate is now achiral. Okay, it has a plane of symmetry right here. The nucleophile has equal probability of attacking from the top or from the bottom. And so as a result, we will get equal amounts of R and S. And we know that as a racemic mixture. So we get racemization occurring if the leaving group is on a chiral carbon in an SN1. Okay, sometimes you don't get exactly 50-50. Okay, there may be some steric factors. Okay, in this case, okay, D here, that represents deuterium, an isotope of hydrogen that has a mass of 2 rather than 1. Right, so we have, this is the carbocation that results. And in this example, we get 40% retention and 60% inversion. So we don't get an exact 50-50. Okay, when we form carbocations, they can rearrange. Okay, so here we have 2-bromo-3-methylbutane, and the unrearranged product would simply have the OCH2CH3 replacing the bromide at this position. But we also get some of this. Okay, carbocations can rearrange to form a more stable carbocation. Okay, this is particularly the case if we have a secondary that can rearrange to a tertiary. Okay, in the Pushing Electrons workbook, there is a section on rearrangement. So I would really encourage you to work through that, to practice how to do rearrangements. The 2 most common types of rearrangement include a hydride shift and a methyl shift. Okay, in this example, since the primary carbocation cannot form, the methyl group on the adjacent carbon will move along with both bonding electrons to the primary carbon, displacing the bromide, and that forms a tertiary carbocation. Okay, the smallest groups on the adjacent carbon will move. If there's a hydrogen, it will give a hydride shift. Okay, let's back up for a minute. Okay, how do we get this rearranged product? All right, so we start out, let me zoom in just a little bit here. All right, so we start out with this compound right here. All right, so the first step is bromide leaves. Right, this is a secondary carbocation. It's directly bonded to two other carbons. And in this example, we would have a hydride shift. So hydrogen is going to pull out both of its electrons, move it over to that positively charged carbon. Okay, so what that accomplishes is it gives us a more stable carbocation. We now have a tertiary. The ethanol then attacks here. We remove a proton. And that gives us that rearranged product. Okay, so how do you decide whether it's SN1 or SN2? Okay, these are some things to look for. Okay, the first criterion is look at the substrate. Okay, if it's a methyl or a primary, it has to be SN2. If it's a tertiary, it has to be SN1. If it's a secondary, it could go either way. SN2 requires a strong nucleophile. Okay, think about how an SN2 works. Nucleophile comes in, it hits the back of the carbon and pushes out the leaving group. Okay, so the faster and harder that nucleophile hits, the faster the reaction. So it does require a strong nucleophile. With an SN1, you can have a weak nucleophile. Okay, because the second step is where the nucleophile forms a bond. That's the fast step. So the rate doesn't depend on that. SN2 is favored by a polar aprotic solvent, whereas SN1 is favored by a protic solvent. Okay, so up here, if we have a secondary substrate, we could shift it one way or the other by choice of solvent. The rate of the reaction is second order for an SN2. It's first order for an SN1. Okay, if the halogen is on a chiral carbon, in an SN2, we'll get complete inversion. With SN1, we'll get racemization or a combination of retention and inversion. Okay, in an SN2, because there is no carbocation intermediate, there's no skeletal rearrangement. Rearrangements are common in SN1 though. Okay, this may be a little hard to read. Okay, so promoting factors. As far as a nucleophile, weak nucleophiles are okay with SN1, but you have to have a strong nucleophile with SN2. Substrate makes a big difference. SN1, tertiary is the fastest, then secondary. Primary and methyl don't undergo SN1. It's the opposite for SN2. You need a good ionizing solvent for SN1 because you want to keep ions separate. For the SN2, solvent is not as important, although an aprotic solvent would promote an SN2. Both of these require a good leaving group, since the bond to the leaving group is broken in the rate determining step. Silver nitrate forces ionization. Okay, we haven't talked about this. Okay, we'll actually have, in a later chapter, we'll have an example of where we have silver. Okay, so I just chose some random alkyl halide. And if I want to make sure that this undergoes SN1, add silver ions. Okay, so this would form the carbocation. As soon as the bromide left, it would form silver bromide. What do you know about silver bromide? Okay, it's really insoluble. Okay, so it would form a precipitate. Which would, of course, prevent the bromide from reattaching to the carbon. So this would force the ionization, formation of this precipitate. Okay, the two reactions differ in their kinetic order. SN1 is first order, SN2 is second order. There's stereochemical differences that we just talked about. SN1, it's a mixture of inversion and retention, whereas SN2, it's complete inversion. SN2 can undergo rearrangement of the skeleton, but SN2 doesn't. Okay, and here is a comparison of the different substrates. Okay, if we have a methyl substrate, it has to undergo SN2. Primary SN2 will be favored unless the R group is exceptionally bulky. And again, you could force ionization with silver nitrate. Secondary could go either way. Often with the SN1, there's rearrangements that can occur. Okay, tertiary halides, they have to undergo SN2. They're too crowded, SN1, sorry. They're too crowded for SN2. Okay, and then the next topic that we'll look at is the other type of reaction, which is elimination. Okay, so that was all about substitution. And I'm going to go ahead and end there. Okay, and I will see you on Wednesday.